So welcome everyone to the Metamaterials Colloquium. Not the normal face of these, but I'm filling in. My name is Claire Dancer. I'm an associate professor at the University of Warwick, and I'm the co-investigator of the Metamaterials Network. And I'm really excited today that I get to chair this session because I really want to hear all about this, not to put any pressure onto Stefan. And to introduce Stefan Szyniszewski, I've probably completely mangled your name, I apologise, who is an assistant professor in the Department of Engineering at Durham University and is one of the co-leads of the Modelling and AI Design Special Interest Group in the network. So Stefan is very interested in bio-inspired structures in nature, in hierarchical structures, and in modelling and simulation in particular, those materials. And I think we're in for a really fascinating talk today on this bio-inspired metallic ceramic non-cuttable material. So with that, I will mute myself and take it away, Stefan.
Thank you, Claire, for this nice introduction. Yes, and thank you for this opportunity to discuss this topic with you and your students and staff. And so basically, this is, yes, the title, and this is the talk I gave at the Institution of Engineering and Technology earlier this year, which explores the links between biological structures and human-made material systems. So as Claire said, I am part of the UK Metamaterials Network, and I'm especially interested in the modeling and design. Anastasia Kisil is the lead. She's on maternity leave now, and Bryn Davies is part of the team, and I think he's here also participating. So I guess to start with something interesting, I want to show you this video of an explosion. And I guess if you look very closely, you will see there is a couple of kind of waves propagating. So I guess my first question to you would be like, why do we have those few waves propagating from the source of blast? You can clearly see 1, 2, 3. And this is like a high-speed camera. So yes, you can write your answers in the chat, for example, or you could also speak up. This is more like to check that you are engaged. So I'm just curious to hear from you. What do you think what those waves are? And there are no wrong answers, and I hope I'm still connected to the call. I had internet problems before.
Yeah, you're fine, Stefan. I can hear you. I don't have any ideas, so I'm not going to venture an opinion. Has anyone else got any thoughts? Cameron, you look willing to say something, but your mic's not working, maybe.
Could be different materials.
What do you mean? That the different medium around the blast source, or?
Different materials exploding.
Oh, you see. So you say it's like a sequence of explosions, right? Like 1, 2, 3. Yeah, so that is a nice try. But maybe to give you a hint, we'll give you a hint. So the explosive, it's located here. This is the actual location that is detonated. So it's basically above ground and at some distance from this concrete kind of test frame. So maybe this gives you now more thoughts or more ideas.
A couple of suggestions in the chat.
Yes, my reflection from the ground plane, exactly. So that's the correct answer, yes. So these are basically reflections, yes. So if you think of the source here, the wave will hit the ground and will reflect, and there are maybe 1 or 2 reflections because the surfaces are not at the uniform distance. So this kind of reflections, yes, they propagate, and we can clearly see those 1, 2, 3. Maybe there's like a tiny 4th one there. But yes, that's a nice video to see if everyone's paying attention. And I was actually on site when the testing was done. I was in the bunker. It was quite interesting experience. Yes, the head count when we are in the bunker before the button is pushed to make sure that nobody is left outside. Quite rigorous health and safety protocols. But yes, okay. So I'm personally excited and interested in architected or architectural or hierarchical materials, and I like this comparison between Egyptian pyramids and an Eiffel Tower, because to me Egyptian pyramid is basically like a bulk material. It's kind of blocks that are packed together, and yes, they have some properties. They seem to be quite durable. And Eiffel Tower is this functional organization of strats, yes, to achieve a much higher, taller structure. That in this case, yes, I think when Eiffel was building the tower, there were no measurements of wind loads. So he had to measure the wind loads himself. It's difficult to design a structure if you don't know much about the loading. How do you size your members without knowing the loading in advance? I think that's why it's such a permeable structure. Like he was trying to really minimize the wind load on it. And apparently the original design drawings are at the Institution of Engineering and Technology in London. So they are in the archives there. I haven't seen them, but you can access those drawings, yes. So in my view, hierarchical structures are resource efficient, and maybe potentially we can advance this field by looking at pre-programmed mechanisms to achieve more interactive structures. And of course, this requires advanced mathematical descriptions, maybe parametrization of those structures so we can optimize them. And they might have multiple benefits, yes, like we basically place the material in optimum locations where it's really needed. And we could also take advantage of strength enhancement at smaller length scales. So as you can see from this description, I'm mostly grounded in like mechanical or metamaterials. I've had projects with fluid flow, but not with optics. But we'll talk a bit about vibrations and waves. The motivation comes from advancements in manufacturing technologies. So this paper is from 2016. That is a group based at MIT, and you can see that they can produce structures from nanometers, so assemble hollow tubes into first-order strats and lattices and hierarchical filaments and unit cells to build hierarchical structures with, here it's 5 levels of hierarchy. So this is already happening, this is possible. Maybe it's not cost effective, maybe it's expensive, and but it seems that we can have those capabilities, and it seems quite achievable. If you look at structures in nature, you will see that that's exactly what nature has done over the course of evolution. And even very familiar structures like Pomeo peel, which we just check in the bin, it's a quite complicated hierarchical structure. Yes, so you can say that it's basically, yes, this is the peel. If you zoom in, it has some kind of spaces maybe for fluid transportation. But then if you zoom in into this porous structure, you will see that it's actually a lattice made of tubes. And each tube is basically a composite material. So it has fibers and matrix. And the same applies to shells. So if you ever been in France, they eat snails there, and they chuck the shells into the bin as well. But if you look closely at those, they seem to have also quite interesting organization of elements. So these are tiles, and they are interlaid with soft material. And actually those tiles resemble ballistic ceramic tiles. If you look at some of the ballistic armors, they're oftentimes made of this kind of hexagonal tiles. And here it seems that the motivation is that interlaying rigid material with soft layers will cause crack arrestation or deflection, will make it difficult for the crack to propagate. So the shell is quite strong, quite tough, even though it's limited by the properties of the building blocks, because that's the main limitation in nature, that nature has only a few kind of building blocks like heating and so on. So it needs to be very clever to achieve best properties, because it cannot just go for the stronger or stiffer base material. And when this asks a question about those levels of hierarchy, there is a group of Professor Mayers in California, and he has devoted few decades of his research career, and he built a nice group of students, and he looks into various structures in nature. An example of his paper is, I think he was comparing feathers of birds across different sizes, so all the way from those very tiny colibri birds, hummingbirds, all to condors, which are quite large. And he found that there is like a common characteristic length scale at some point. But yes, I'm not showing this here. So one of his projects, or his kind of explorations, was this investigation of levels of hierarchy, right? So if you think of those levels of hierarchy, it's like this Russian dolls, where you have doll inside a doll and a doll and so on. So if this is the first level, and then maybe, yes, so each tile is made of smaller tiles and soft material, and then the smaller tile is made of even smaller ones and so on. So his observation was this: as level of hierarchies increases, the toughness increases, but the strength drops. So we have more and more kind of porous material, and then it's easier to fail it. Or, but there might be like a kind of Pareto front or a trade-off. Yes, maybe his observation was like 4 levels of hierarchy would be like a sweet spot where both strength and toughness is good. Because you might have a very strong material, but it shatters under impact, for example, or maybe very tough, flexible material, but it's not very strong. So I think these are interesting kind of investigations. And if you look at the biological structures like the seashell, yes, it has calcium carbonate, but also chitin molecular chains. And those chains forms, yes, those mineral bridges. There are different types of bridges and connections. And even those heating fibers, you know, they look a bit like kind of networks of connections. And then you can build mesolayers, and then you look at the sea creature shell, which I guess looks nothing really, not really that special, but actually those levels of hierarchy are quite incredible. And what I find interesting there is that these structures have evolved over, I don't know, hundreds of millions or so, very long time, very many kind of evolutionary cycles to find structures that are very functional. And I feel this is our challenge with human-made materials, that we have so many possibilities, but we cannot wait for 1 billion years to deliver a product to the customer. We only have 6-month cycles or annual cycle or 3 months. So how do we perform complex designs on such multiple kind of physical domains, levels of hierarchy in a rational way? I think that's a big challenge. So the specific material I want to focus on in this talk is metallic foam with ceramic inserts. So I have been working with cellular metals for a long time, maybe a decade or more, and developing material models, modeling. And I was once in a meeting with a person from the Home Office, and they were looking for a solution to stop angle grinders, because they said the battery-powered angle grinders could become a problem for many security installations. And it occurred to me at the time that why don't we try to emulate the abalone structure, so stiff soft organization, using cellular metal and ceramic spheres. And maybe that is maybe that will work. So it will be simultaneously lightweight, but difficult to breach or to cut. But the principle here is different. I mean, we need to stop angle grinders. It's not a conventional type of loading. So then I thought that maybe we can use local resonance and vibrations of those spheres. If you look at those, you can say this is mass immersed in a flexible matrix, so it should be susceptible to local resonance. And that might be our resistance mechanism, dynamic one. So how do you make those materials? So it's a little bit like baking. You mix metallic flour with baking soda, some kind of foaming agent, you mix it, then it's pressed. So this pressing ensures that the interfaces are in close contact and extruded. After extrusion, it looks like a solid bar. You know, you wouldn't tell that this is just compressed powder. And then it goes into the oven and the foaming takes place. Material really expands, so it needs to be kind of in a watertight container. And then you end up with the sample. So that's what you end up with. This is this top left corner shows this is a CT scan of the manufactured plate. This is a cylinder. This is also a CT scan. So you end up with structures like this, and I think we can produce them in many different ways. I mean, 3D printing could also work with inverse casting and so on, but it would be more expensive probably. So as I said, I'm interested in modeling, and if you think of like a hollow sphere foam, even such relatively, simple problems like compressions, they are quite challenging computationally. So in this case, I used LS-DYNA, and I had to reach for help to developers because there were so many conflicting contacts here. Like if you think of the contacts, there are maybe, tens or hundreds of simultaneous contacts there, and they might give like conflicting directions for the iterations because the contact says, let's push this out, but then you push the sphere into another contact plane, and they can get stuck in like endless cycles there. So that's an example of, yes, real life kind of test, which is causing numerical problems. But finally, it's possible to resolve it. So the advantage of this is that if we do such models or simulations, yes, we can maybe get good, decent comparison with experimental data. So you can see comparisons, they are not great, but not bad. And then by looking at those sections, yes, it becomes apparent that it's actually buckling of spherical shells that governs the mechanical behavior of such kind of sintered foams. And the buckling capacity depends on the radius of the shell, its thickness, and parameters. So then we can draw some kind of conclusions. And in this case, we are looking at sensitivity to temperature. So what happens if you heat it up? And it turns out that the buckling is controlled by the yield stress because we are in the plastic buckling regime. So the temperature dependency is a function of yield stress, kind of, not the Young modulus. But for a very thin shell, it could be controlled by elastic buckling, and then it would be like a reversible, like a sponge that bounces back, but those shells would need to be very thin. Okay, so returning our attention to the primary motivation that was given by the Home Office. So they said, look, those items can be purchased for 30 pounds, and this is what happens when you try to cut armor plate. So this is, I think, 12mm armor plate that is used in tanks. So it will stop handguns and machine gun bullets. Yes, the video is a bit choppy. Maybe it's because I'm streaming it. But you can see that you can cut through this probably in a minute or so. Yes. Now the sparkles are coming on both sides. And if I stop it here, yes, the blade went through. It's a bit grainy video, but I hope you trust me, yes, that you can cut steel. It takes some time, but it's not such a long time. I mean, if you want to cut an opening, maybe you need a few minutes and it can be done. And the motivation is, this is an example from one company that approached us later on. So these are bike sheds in London, in Camden. And you can see that a criminal can come with an angle grinder. They just cut this plate, they open it, and they steal 8 bikes, for example, right? So that's the cut lock. So they were looking for a solution for this problem. So this is our plate, which has a cellular metal and ceramic spheres. This test was done at the Center for Applied Science and Technology in Langford. Sadly enough, I think the center is closed now, like due to budget cuts or consolidated with another center. But yes, if you look at this video, you will see that there is initial penetration, but then things stop and the blade is gone. But the disc is no more. Yeah, hopefully you have seen that the radius shrinked. And from the big disc, there is no disc. So how does it work? So this is the principle that when you try to cut it, basically as the spheres start vibrating, but also they will be partially grinded. So we end up with this vibrational interface, which is a bit like a sandpaper. So basically vibrating sandpaper. And yes, we had some kind of media attention after that. I think it was a bit overblown. I wish it was a bit embarrassing actually. But I think if you look at the cross section, the CT scans, what happens? Yes, you see there is partial penetration, but then it gets stuck because once it engages the sphere, the vibrations kick in. So here we were like going for the material, and this vibrational mechanism is the key resistance mechanism. So it's not the hardness of the spheres. So why does it work, right? The interesting thing is that the disks naturally vibrate. If you have a rotating disk, there are eigenmodes of the disk, and the waves, I will tell you more about this in a moment, but they are standing waves, and those modes are quite interesting. And also we have natural frequencies of our material as well. So there is a natural frequency of the sphere in the soft medium, and if you have more of them, there will be some interactions there. And it's a coupled problem probably. So if you go back, the original work on the vibrations in disks, rotating disk, was done by Wilfred Campbell, who was an engineer working for General Electric. He was developing the steam turbine disks. And I think he was the person who made them successful as a company. But unfortunately, he didn't live long enough to respond to reviewers' comments. So when you read the original article, it says, owing to Mr. Campbell's untimely death, very shortly after the presentation of this paper, the closure is prepared entirely by Mrs. Kimball and Robinson, but includes the remarks made by Mr. Campbell at the meeting in answer to Mr. DeWolf. The short time allowed at the meeting prevented the author from replying in person to any other discussion at the time. And yes, unfortunately, he seems to have died in some kind of accident, so was not able to respond to all reviewer comments. But I think personally, I would credit him for the success of General Electric, now a huge corporation, multi-billion, because basically he solved the problem of failing rotating disks. So what he recognized was, and I think he was very ingenious. It was not easy to find the original paper he published. I think it was 1920 something, 24. Very few manuscripts left. I had to get a book from the University of Cambridge because my wife used to work there at the time. But it's a fascinating article. It's about 60 pages of very rigorous work and incredible inventiveness. So if you look at the article, yeah, so this is the failure of steam turbines, because basically the way they were testing them, they would look for natural modes by basically having sand, like pouring sand on it and then vibrating it. And once you reach some natural frequency, you will see there is a resonance, and the sand will show you what is the shape of the eigenmode. But this is vibrational mode of a stationary disk. When the disk rotates, this mode is it's not the same frequency. You can see all the modes. Very clever, without finite elements, using simple kind of electrical switches and sand. And these are more complicated modes. These are interesting, yes. I'm kind of really higher modes. So you could see that. And of course, they were trying to estimate those modes. But what he has realized is that actually those modes consist of traveling waves, which I find quite fascinating. Yes, so if you look at the disk, there are two waves that travel in the opposite direction. So one wave is traveling with the rotation and the other wave is traveling against the rotation of the disk. And they overlap. So this is like his sketches of how the waves overlap, and they form a standing wave because they move in the opposite directions. So if you are sitting on the disk, like on a merry-go-round, you will see a standing wave, yes. But if you are an external observer, you will see two waves. You will actually be able to record that one wave is faster because it's rotating with the disk, and the other wave is slower because it's moving against the rotation of the disk. So there are actually two frequencies that depend on the speed of the disk. So the faster the disk rotates, those two frequencies, one gets faster, the other gets slower, and they can get in resonance. So the disk could get in resonance at the lower frequency than predicted, and also the higher frequency, depending on the speed of the disk. And they didn't know that before his work, and the disks were failing and nobody could figure it out until he did his experiments with like clever kind of measurements, yes, externally with the magnets and like with a disk rotating with the disk. So just to reinforce this message, yes, so these are kind of the stationary modes, and they are two types of modes, so kind of radial modes. So on the right hand side there are radial modes, but there are also those modes that kind of go around the circumference. And I think they introduced notation at the time is that there are like two numbers. So if this is 2, it means that it's like a second mode. There are two lines that can divide kind of the waves. And if S is equal to 1, it means that there is like one circumference. So there is one wave along the radius. So it's kind of like a polar system of coordinates, that the waves could have waveforms along the radius or along the angle rotation. And there could be combinations, yes, like this N1, S2. So that means, yes, there's only one line dividing it. So there's one wave going around the circumference, but this wave is broken into kind of like sine wave from the center of the disk. And the opening will affect the waves as well. Yes, if you cut a bigger opening, it will have an effect on those waves. But the interesting thing is that, yes, if you look at the multiple waves, so say we activate a few waves at the same time, the signal becomes kind of a little bit chaotic. So this is a CT scan that shows, what might happen when the disk tries to cut the material. So that's the disk. That's a cylindrical specimen that we used for. We needed a cylindrical specimen to be able to do a CT scan, like a proper one. But basically, when the disk encounters the sphere, we start activating all those natural frequencies because it's like an intermittent contact. It's like basically hitting it. And those waves that travel around will face an obstacle, right? So the waves, traveling waves, will be disrupted. It's like a wave breaker now on their way that is kind of disrupting these waves traveling back and forth. So there is definitely a highly vibrational interface there. The energy is supplied by the disk itself. And now this vibrational interface is like a sandpaper, which is grinding the disk. So why the sandpaper is important? So this is like a schematic, yes, that we cut it. It goes into vibrations, and the waves are there no matter what. The waves face an obstacle. and we have traces of the powder. And it's a quite big range of particulate matter. So these are smaller images. I think here those bars should be down, but yes, this is micrometers. I think this is 100 microns. This is 20 microns. So you can see fiberglass. So fiberglass comes from the discs. Iron shards, also some kind of aluminium parts. So a lot of kind of, and that's an interesting image. Yes, we used low-cost ceramic material because we were short on funding. We had very little budget, but it was a good choice at the end because it kind of promoted this fragmentation into particles. So that was an even more abrasive interface. And there is another effect that I don't know if I included this, but you may see sandbags in the war zones because particulate matter becomes very stiff at high rate of loading. So if you load particles at very fast speed, there are some repulsive forces at the interfaces which make up material very strong or very, hard to pierce. If you apply loading very slowly, yes, it's not that resistant. That's why you see gravel or sandbags, because they are, yes, quite very effective for fast-moving projectiles. So yes, the faster this interface, the harder it also becomes. So I guess to start drawing to the close, so I don't go too much over time, I feel that we use this term metamaterial, and we had discussions with Claire what metamaterial is, and it's not an easy definition. But yes, I feel that it's this hierarchical structure that the organization of different elements is for some reason, and we could maybe develop more complicated things. And there is very active community developing biological soft robots, which respond to environment, pre-programmable material systems that react to external stimuli. I think there are interesting questions about circular economy and recycling and reuse, because if you think of biological structures, they use very few building blocks. They achieve properties through spatial organization. If you think of structural colors, yes, colors are achieved by the structure of the surface, not by using some rare minerals or rare ingredients, because nature has to find ways locally. It cannot go very far away to source a little bit of something it needs. And so I think maybe that's also an opportunity for us to start designing things for smart structures, and maybe with fewer base materials and with more thinking about how to recycle them. And I feel in the long term, there is also a potential for kind of blending the boundaries between what we make and the natural structures around us. So if the materials become responsive, they become almost like interactive with environment, with things that happen around them. So maybe the environment also begins to kind of sense this interaction, and yes, it might be a two-way connection, but maybe that's kind of too futuristic. Yes, I think that's the last slide. So I guess I will stop sharing. There is a question in the chat, and I will now switch to questions.
Thanks, Stefan, for a wonderful talk. It's really interesting. Fascinated by this material. I can't see any questions in the chat. No, one has appeared. Absolutely. So please do put questions into the chat if you'd like to, or you can put your hand up and ask them yourself. Londono, did you want to ask your question yourself? You're very welcome to.
Yes, you can unmute yourself and you can ask. I can also read out the questions out loud.
Hello. Yes. No, thank you very much for.
Oh no, not sorry.
Can you hear me now?
Yes,
thank you very much, Stefan, for your presentation. Very interesting research, and the material is quite interesting. So my two questions is first about cost, how this compared with steel, which is what you compared with, guys. And my second question is, if you cannot cut it, how do you produce something with that material?
Yes, these are good questions. So thank you, Londono, for those questions. The cost is about, I would say, maybe 200-300 euros per square meter. So it is maybe, 5-10 times more expensive than steel. So steel is super cheap, I think. But if you compare it to ceramic materials like ceramic plates used in armors, maybe it is 10 times cheaper. So I would say it's kind of like halfway. I mean, steel is really like a mass commodity. It's it's probably cheaper than carrots or per kilogram and so on. It's hard to beat the cost of steel. I mean, concrete is the same animal. Like I think it's almost impossible to have something cheaper than steel in terms of like, or yeah, maybe composites could be cheaper. I don't know, but I think everything, I feel like steel is hard to beat. But I still feel that the cost of 200-300 euros per square meter, yes, sounds like a lot, but maybe if you think you could make 100 bike locks or 50 bike locks in a square meter, and maybe the bike lock to make costs 30-40 pounds and you sell it for 80-90, maybe then it makes sense, yes. Or so I would say it is a problem. Yes, it's not like obviously cheap, but I think it's not prohibitively expensive. But yes, it's a challenge to reduce the cost. And I think there are two challenges. Ceramics are not cheap, and also energy is also costly now. Like you need heating, you need melting, and so on. The second question, how do you mold it? Yes, I think you need to have, you need to know in advance what your shape will be. So say with bike lock, yes, you can just mold it in the U shape. You don't have to cut it. You have like parts that can be molded before. Maybe you can cold form it, so you can bend it. It's like a steel plate, so it can still be like bent and cold formed. If you need drills, you can place like a placeholder. And then, you can drill through those placeholders if you know the location of the openings in advance. If you are not sure about your edges or tolerances, again, there could be like a solid metal there and you can trim it and adjust it. But yes, there is no obvious way to make like huge panel and cut it into smaller ones. No, that is problematic. And there was a question about auxetic materials. I think that's an interesting idea, yes. And that basically, as you have the material that stiffens under the loading. I think vibrational loading is not that powerful. I mean, it's just the force of a person that is pushing the angle grinder. So maybe you don't, I guess if it was a soft material, it could, the foam is not as soft, like you cannot indent it with your finger. It is still a quite stiff material. You probably need like a hammer or quite significant force to like start compressing it. I think it's an interesting idea, could work. The question would be then, how do you manufacture it? So with the powder metallurgy, it's like foaming. It's much cheaper. If you want to 3D print exotic kind of shapes, then it will become more expensive. So maybe the performance improves by 40%, but the cost increases by 500%, for example. So that's what I've seen, this trade-off. There is another question about...
So Cameron's question, I don't think Cameron's microphone is working unless it is now. No, it's not. Sorry, Cam.
Yeah, so there is a question about
frequency.
Yes, and changing the RPMs will compromise. So I think the interesting feature here is that we are not exactly in resonance. Like we looked at the frequencies of the disks and the frequencies of the spheres. We are in the same order of magnitude. So basically, they are hundreds of hertz or they are close to each other, but they are not. I think here the problem is that the sphere is becoming like a wave breaker, because when the disk rotates, it basically all the waves start hitting the interface at some point. So effectively, I believe that, yes, whatever discrepancy there is, there will be still this transient excitation at the interface with the sphere. It's basically like if you think of the old-fashioned, what are they called? The music discs. I forgot the word. Records, yes, like those old records, right? And if you push it with a finger or with something, you will see it will start shaking. And this will happen irrespectively of the natural frequency of the disk. It's just kind of this disturbance that is now on the way, disrupting how the waves, and this disturbance is moving, because you can think you can think it's a relative movement, right? It's either the disk is stationary and you're moving your finger around, or you can say my finger is stationary and the disk is moving around, right? So if you view it as a stationary disk and the obstacle moving around, this will excite vibrations because it's basically a point moving around the disk, which, so I think the nature of this interface is just exciting those frequencies anyway. And because it's same order of magnitudes, they start interacting. That is, the interaction is strong enough. And actually the operators reported the vibrations. They said you can sense it, like, the tool is kind of jiggling in your hands. It's hard to hold. So yeah, it's definitely like beyond any doubt that this happens. Yes.
Super interesting. So no more questions. So I'm going to jump in with my questions because I get to do that because I'm So obviously, Stefan, you probably know that I most of the time when I'm not being a metamaterials person, most of my research is on ceramics. So I'm really intrigued about this. And some ceramics are incredibly cheap, actually. You say they're expensive, but
I think 20 euros per kilogram. That was alumina, Al2O3.
For alumina, yeah. But if you think about, one form of ceramic is sand. That's extremely cheap material. You mentioned that you don't think it makes much difference which material it is. Is that?
I think it shouldn't make a huge difference, yes, as long as it's, yes.
But you need that regularity of sphere, and that's the important part of it, the regular shape and distribution of the particles.
Yes, we need to keep basically the arrangement, yes.
Yeah,
so it's
but
kind
the
of
actual
regular.
material is not so important. So it's very intrigued. The other thing I wanted to ask about was on the final slide, you mentioned the importance of the circular economy and the importance of being able to recycle and reuse. Now, you've got a system there that's a ceramic in metal, which may not be the best combination for recycling. I was wondering if you could talk a little bit about some of the challenges with that and how you might replace the materials, for example.
So actually I might be wrong, but my thinking was that we can simply melt the aluminium and recover the ceramic spheres from it. So I think the recycling should be quite straightforward. Yes, you just throw it in the oven, you melt the aluminium. I don't know how you can kind of drain it safely. And then you have maybe like a ceramic sieve or something that has higher melting point and will catch all those spheres, and then you can reuse them again. So I think it should be recyclable as it is now. Yes,
so not so bad then.
Yes, and I think we can use aluminium chips. So machining chips can be used for foaming. So I was talking about metallic powder, but I think we could use machining waste, all those chips that are waste from all kinds of machining processes.
Okay, yes, sorry. Yeah, I see what you mean. Yes, the sort of leftover bits that are
yes, the little kind of thing. So yeah, that could be used. And I'm also very interested in talking to you, Claire, about ceramics, because I was looking at sources of recycled ceramics. Like I thought about, say, grinding media. I know that there are grinding kind of spheres that are used for grinding ceramic paints. Yeah. I don't know what happens with those at the end of life. If you can take
a lot of it goes down the drain, if I'm honest, in the system. Yeah, there's a huge amount of waste there, and the other place there's a vast amount of ceramic waste. If you're looking for ceramic waste, is in the steelmaking industry. There's a lot of refractory materials that get generated as byproducts, and if you go down to a steel plant, you'll see piles of it everywhere. It's literally like just rocks that are piled up. So yeah, ceramics are quite an enabling technology, and they get sort of used and then discarded. And what to do with those wasted things, it would be good to have a better source of a better thing to do with them. So yeah, we should talk.
Yes.
I've got one last general question, but if anyone else has got a question, please jump in. We're almost at the end of our time, but if anyone's got another one, put your hand up or put it in the chat. But I did want to ask you one more thing, which was obviously this structure is the abalone. Sorry, this is the abalone shell structure that you've been mimicking. Are there any other structures in nature which intrigue you, which might be something for a future system?
in terms of like mechanical systems.
What's an interesting structure that we might be looking out for in the future?
I think there are two structures that I find fascinating. So timber and fibers in plants and wood, because I think they are very compatible with composites. Composites are also made of fibers. And if you think of trees, when they are very young, they are very flexible, because they need to be flexible. You know, if there's like an animal or something, they are not, but if you look at the big trees, they are not flexible anymore. They become rigid. And they do this by adding layers of fibers at different angles. So the initial layers are like at 45 degrees, so they are flexible. And then they start aligning more and more layers with the loading direction. So they stiffen as they grow. And I think there are many interesting parallels, yes, between the world of plants and the fibrous structures. And
it sounds a lot like layup, that you do layup for composite structures. You sort of put one layer in different directions. And
yes, but also they respond to humidity. So you may see that they change directions of the leaves, for example, yes, in the sun, and this is in response to humidity. Maybe we can have composites that respond to humidity or other conditions, yes. So I think there are interesting solutions in that space. The other interesting hierarchical structure is feathers. I think they are quite interesting. So for example, I don't know if you know, but most of the bird's feathers, they have this kind of mechanism that when the bird moves the wings up, they open up like microcells, so it becomes permeable. And when it flaps down, it closes down. So it's like an adaptive mechanism that will open and close. And interestingly, the length scale of this mechanism is the same across all birds, from the tiny ones to the huge ones. And I think if you think of owls, they are super quiet, but they have porous wings. I feel like we can do more in terms of like aerodynamics. I think our structures are smooth, rigid. Like if I look at automotive or airplanes, I think there is some room for more complexity, more hierarchical structures there as well. Yes.
Fantastic. Well, we are at the end of our time. So thank you so much, Stefan, for all of your wonderful talk and answering everybody's questions so well. And thank you to everyone for coming along as well. And hopefully you'll be back again for another colloquium sometime soon. So
thank you
very
guys.
much.
It was a pleasure.